So in this video, we'll be looking at the example of a golf ball rolling off a cliff at an angle. So the problem says that the ball rolls off a 60-meter high vertical cliff, and it has a speed of 25 meters per second. So that's our initial velocity. It's rolling off the cliff at an angle of 15 degrees below the horizontal. And then we're asked how far from the cliff's base does the ball land? So how far? So we're looking for a distance. So I have a simplified diagram here drawn where we have this golf ball on the edge of the cliff, and it's at this decline angle, and it goes off and it becomes a projectile, and then it lands some distance from the base of the cliff. So let's draw our coordinate system. And I'm going to draw it where the origin is at the base of the cliff here. And to the right is going to be the positive x direction. And up is going to be the positive y direction. And so now that we've labeled our coordinate system, we can start filling in the initial values that we know and don't know. So the ball's moving off the cliff at a velocity v0. The initial position x is equal to 0 meters. The initial y position is equal to the height of the cliff, which is 60 meters. The final position of the ball, it's going to have a final velocity pointing down and to the right. We don't know what that velocity is going to be. The final x position, we don't know what that is, and that's actually what we're looking for. And then the final y position is just equal to 0 meters. Some other information we know: with projectile motion, the acceleration in the y direction is equal to the acceleration by gravity, which is negative 9.8 meters per second squared. We're not giving any information about time, so time is going to be a question mark. Our next step is to draw our initial velocity diagram and break it up into its x and y components. So starting from the tail, we draw our x component. That's v0 x. And then from the tip, we draw our y component downwards. And that's v0 y, v0 x. Okay, and now we're going to draw our angle. We are 15 degrees below the horizontal. So that angle is 15 degrees. So now we can solve for our components using SOHCAHTOA. So v0 x is equal to 25 meters per second. This is the adjacent, so cosine of 15 degrees. And then for y, we have v0 y is equal to 25 meters per second. And this is the opposite side, so sine or so 15 degrees. And that comes out to negative 6.47 meters per second because that's downwards. Of course, you don't need to include that negative sign when you're drawing it next to the vector because the vector is telling you that it's pointing downwards, so it's negative. I personally like to include it just because it reminds me that v0 y, the initial velocity in the y direction, is in fact a negative number. And then for the x, solving for that, we get positive 24.1 meters per second. So now we have all the given information done. We just need to define what it is we are looking for. And so what we're looking for is how far from the cliff's base does the ball land. So we're looking for a distance, and we're looking for this distance in the x direction. So from the origin to the final position, we're looking for this distance right here. And so we're looking for what XF is, and we're expecting a positive value, and we're expecting units of meters. So our next step now is to plan the solution. So based off of the givens and the unknowns, we need to choose the equations that are appropriate here. So in the x direction, this is projectile motion. We know that the acceleration in the x direction is 0. So we have the equation in the x direction is the final position is equal to the initial position plus the initial velocity multiplied by time. We are looking for this final x position. We know the initial x position. We know the initial velocity in the x direction. We don't know time. So we're going to need another equation that solves for time to be able to use this equation. So moving to the y direction, we want an equation with time. We know positions and we know the initial velocity. So we choose the kinematics equation that's a position as a function of time. So we have y, final y is equal to the initial y position plus the initial velocity in the y direction multiplied by time plus 1/2 the acceleration in the y direction multiplied by time squared. We know the initial and final positions in the y direction. We know the initial velocity in the y direction. We don't know time. We know the acceleration in the y, and again, we don't know time. So one equation, one unknown, we can solve for that, and then we can use that in the x equation to solve for the position. So now we just need to carry out the plan. We're going to start with the equation in the y direction so that we can solve for time. So substituting everything in, we find that, I dropped a squared here, we find that we need to use the quadratic equation. So substituting everything in, we're left with t is equal to 6.47 meters per second plus or minus 34.9 meters per second divided by negative 9.8 meters per second squared. So if we choose the positive value, we're going to be left with a positive number up top and a negative number on the denominator. That's going to leave us with an overall negative time, which doesn't make sense physically. So we need to choose the negative solution. So subtracting and dividing, we find that the time it takes for the golf ball to reach the ground from its launch point is 2.90 seconds. Now that we've solved for the time that the ball is in flight, we can use our equation in the x direction, the second equation, to solve for the final position of the golf ball. Substituting in those values, we find that the final position is equal to 69.9 meters. So to answer the question of the how far from the cliff's base does the ball land, the ball lands 69.9 meters to the right of the cliff's base. Now checking our work, we have a complete solution. The sign is positive as expected. We have units of meters for position, which is good. And this magnitude, so this is roughly 200 feet. The initial velocity in the x direction is 24.1 meters per second. 24.1 meters per second, which is roughly 50 miles an hour. So it's not surprising that the ball travels that far of a distance because the velocity is pretty large. So the magnitude does seem reasonable.